My name is LeAndra Nelson, and I'm a hydraulic engineer with Kiewit Engineering Group. I had the opportunity this year to collaborate with Kiewit Construction on a project in which we took drone images of riprap and were able to measure the gradation from those images. Before I get into that too much, just a little bit about Kiewit Engineering Group. We're actually made up of roughly 1,400 engineers within several disciplines of engineering. We provide construction engineering services for temporary design during construction, as well as permanent design services. And in this case, we actually didn't design anything, but we were providing our own internal QC for the project. One thing Kiewit is big on is innovation, and we're always looking towards the future. And on this project, the district was worried about whether or not we were going to pass our inspection, and current processes for measuring rock gradation can be limited. There was already drones being used on the project, and we were able to build on the use of the drones that were already there to provide ourselves our own independent quality check. So we use US 34 Permanent Repair Project as a case study for this. This project is located in Big Thompson Canyon, which is northwest of Denver, Colorado. This video shows some of the highlights of the project and gives some interesting facts on the project. In 2013, there was a massive flood which took out several of the roadways. It killed 8 people and caused a lot of damage. This isn't the first time that this area is flooded. It also flooded in 1976, which resulted in 144 deaths and, again, a lot of damage. So Kiewit was hired as the contractor. Again, we didn't design anything, but one of the purposes of the design was to leave a 15-foot roadway in the event of another flood. And to do this, they realigned some of the roads within the canyon, and they also used some matrix riprap and some new innovations on the project altogether. The corridor was 26 miles long, and soon some before and after pictures will come up that show some of the damage and the repairs that Kiewit was able to implement based on the design. There was a lot of collaboration with different agencies. These are the before and after pictures. There's a lot of collaborations with different agencies, and I know a lot of those people are in this room today, so just thank you to everyone that was a part of this. And the canyon was reopened earlier this year to the public. So because this project was so important and so large, there was a lot of technology on the project, and one of those was making sure we had adequate GPS coverage on the project. And to do that, we used real-time kinematics so that the surveyors were walking around with the probes and automatically updating where they were in real time. The machines were also equipped with GPS so that they would know where exactly they were within the corridor. And drones were used on the project to create topographic models for construction work planning as well as quantity determination. One of the biggest challenges on this project was the embankment protection. Again, it flooded out some of the roads, washed out the roads, and one of the goals was to leave that 15-foot roadway in the event of another flood. As the legend on the right shows, there are several different gradations and types of riprap that was used. Traditional riprap ranged in size from 12 inches to 36 inches, and matrix riprap was used in 12-inch and 18-inch gradations. So the plan view on the top just shows that there was a lot of variance in the gradations that were used on the project, and they were right next to each other, so that's where some of that GPS comes in important with the machines to know where you are within the corridor. Over 100,000 cubic yards of riprap was placed, and because it's in a canyon and there's some narrow corridors, there is very difficult placement. Sometimes the machines were within the river itself, installing the riprap on the stream bank. Again, in the last slide, we saw that there was varying gradations throughout the project. So the district was worried that we were going to fail inspection based on some of the accepted QC methods. Those accepted QC methods are visual inspection, bulk weigh, and random sampling. These three images show the 12-inch, 18-inch, and 24-inch riprap gradations. Basically what the inspector is going to do is they're going to look at the placed riprap and compare that to these inspection piles and determine whether or not it passes specification. The second QC method is bulk weigh. For this graph, we compared 4 samples that were weighed on the project of 18-inch riprap. The average sample size was roughly 50 stones, and one of the limitations in this sample or in this method is that you're missing some of the larger stones as well as some of the smaller stones, and the two lines are showing the upper and lower limits of the gradation. The third QC method is random sampling, and basically you're going to measure the diameter of the rock at uniform intervals. This is actually showing strictly the diameter measurement, and one of the limitations with that is that the specification is based on mass, and so we have to account for the mass in this rather than just the actual gradation or the diameter itself. So this graph looks great, but when you correct for that volumetric conversion, this is what the graph looks like for a 12-inch gradation. And so maybe this won't pass inspection. But then when you compare this 12-inch of random sampling to a 12-inch riprap gradation based on bulk weigh, the bulk weigh is probably a little more accurate. However, all these methods have their own drawbacks. Visual inspection, it requires an experienced inspector. Again, you're going and the inspector is deciding themselves whether or not it's going to pass inspection. The mass weigh is time consuming, and you also have a large mass that you're putting into a truck, and then you have to drive to the weigh station and then drive to the site. And then random sampling, you have to perform that volumetric correction, and for both of those, the sample size is just too small to be reliable. So when the district called us, we performed our own independent quality methods. We used ground level image segmentation as well as drone image segmentation. So this is the ground level image segmentation. This was a 12-inch sample, and we were able to take a picture at the ground level, and this sample is probably roughly 250 stones. So already just in one picture, your sample size is 5 times that of the bulk weigh or the random sampling. And what the program does is it delineates the rock faces and the rock edges, and from that it can measure the size of all the rocks that are in that picture, and then it will output a gradation curve. So for this sample, it was a 12-inch riprap gradation. Our D50 was roughly 14 inches, and there's about 39% passing the 12-inch gradation. So this is pretty accurately placed. But we can take this a step further and use drones to measure the riprap gradation. So again, we have that comprehensive GPS network. When we flew the drones, we made sure to include control points. So the picture on the left shows that for this image, we have 8 control points throughout the corridor. And then the picture on the right shows the aerial images that were captured on that drone flight. For this image, there's 234 images that were stitched together in the program to create the one image. So how do you fly the drones? The typical flight height on this project was 80 meters and 120 meters. We were also able to have them fly some of the drones at 40 meters. So these 3 pictures are comparing the resolutions at those different flight heights. 40-meter flight height is obviously a better resolution and going to have the least amount of vertical error. The 80-meter flight height, you can still tell that there are rocks in the picture and you can see the rock edges and faces, so it's probably going to be pretty accurate for the program as well. And when you get to the 120-meter flight height, it's a little pixelated. You can't necessarily tell what's a rock and what's not, so not quite as accurate for this use. We used a Kiewit operator with a surveying background. Again, they were using it for topographic purposes, so that's why they already had that surveying background, but it is important for this purpose as well. It provided a roughly 3 to 4 inch accuracy. We needed to make sure that that pilot was an FAA licensed pilot. We wanted to make sure we're meeting all legal requirements. The best time to fly these drones for this purpose was midday and during like sunny conditions, because since we are in the canyon, there's trees, there's the canyon walls that could cast shadows onto the riprap, and that could hinder the image quality. And so the drones, we were able to program those based on the GPS so that they were flying over those control points that we provided. And again, it's taking those 234 images and we put them into a program to stitch those images together. So that's how they were already flying the drones, and we were able to take that, which they use for those quantity and topographic purposes, and use that to prove to ourselves that we're meeting gradation quality, using the processing results and then taking that, putting it into a different program, and outputting some gradation classes. So those 234 images were stitched together to create this one single image. And then since they were using it for topographic, we were also able to create a DTM based on that. Once we had that full image, we were able to extract a scaled image, which we chose a 100-foot by 25-foot sample. And it's important to note that since it was GPS coverage, this is a geo-referenced image, so I was able to bring it into Google Earth and confirm where I was within the corridor, and from that I can compare that to the plan sheet, and I know what gradation I'm looking for in this sample. And for this particular image, it was supposed to be an 18-inch gradation. So I took that 2,500 square foot sample area and I put it into the program. This sample contains over 1,000 stones, so we're getting even more reliable results, and it's a better sample in general. Again, the program is delineating the rock faces and the rock edges. The picture on the right is just a blow up to better see those delineations that it's making. So we added the scale, the 2,500 foot scale and square foot 6, and then it outputs the 18-inch riprap gradation. In this sample, we're getting a D50 of 17 inches with about 55% passing the 18-inch gradation. So we're proving to ourselves in this instance that we're meeting specification. From that, Kiewit is big on keeping track of all of our samples and tests and everything. So we have a program at Kiewit called KeyTrack, which we can upload the documents. This is one of our sample gradation reports that we created. Some of the important things to note were the weather conditions. Again, we wanted midday with clear skies. We noted the station within the corridor and the plan D50. I also provided that picture that we used in the program so that we can compare if we ever need to go back. We also provided an area where we could compare, say the random sampling or the bulk weigh was done at the same time as the drone was flown. We can compare, we can say which test was performed, whether it passed or whether it failed, and also provide the D15, D50, and D85. And then we also just said it matches the visual inspection and passes specification. So we upload that into the program and we can come back and look at it whenever. Again, that sample size of 1,000 stones is going to give you a more reliable analysis compared to the traditional QC methods, as well as compared to just a ground level image segmentation. This project was easy to integrate with the drone survey that was already done. We were able to take flights that were already performed and use those images to put them into our program to prove to ourselves we're meeting our own independent QC. This allows Kiewit to build their project right the first time, and that reduces the risk of schedule overrun or cost overrun. And safety is also an issue. If you have someone out there measuring the diameter of rocks, that's an unstable surface. Someone could roll their ankle or fall or something. And then also if you have these large gradations in the trucks that's driving through a canyon, you just want to reduce how long they're actually driving through that canyon. But at Kiewit, we have this kind of motto that we're pleased but not satisfied. So what comes next in the future? Like, we proved to ourselves we're meeting QC with this method, but how can we do it in the future? So since we had topographic survey and we had aerial images, we were able to overlay that image onto a point cloud and then extract that image to make a 3D image. Once that's done, you can isolate the riprap area, and then as this is going to do, it's going to isolate a single rock with the point cloud, and then once that rock is delineated, it'll isolate itself. And then you can take that and you can determine the volume of that single rock. So in the future, when you have a whole point cloud full of a stretch of riprap, you can take the entire location and measure the whole volume from that, and then potentially get an even better gradation analysis. There are also other point cloud applications. They used it for quantity takeoff. We were just proving that we can use it for quality assurance. Point clouds can be used for work planning or to determine some bridge clearances, and also with automatic object identification, so you can determine whether something's a rock or a street lamp or a door, depending on what project you're working on. So the whole idea of pleased but not satisfied is something that's been a part of Kiewit for a while. And this is just a quote from Peter Kiewit, that growth and improvement are not likely to occur unless we are willing to try something we have not done before. Sometimes the effort fails, but it is the reaching, the striving, the divine discontent that builds confidence and generates greater strength and knowledge. I'd like to thank George Cotton, Ben Constable, Jim Brinkman, and Carl Pearson for their help with the data acquisition, data analysis, and the several questions that I had throughout the process. So thank you all for your time and attention, and do you guys have any questions for me?
You said you also did some ground-based photography or photos acquisition. What did you use for a camera? Is that?
I believe just an iPad was used to take the image. I don't know who.
What software did you use to analyze it?
It was called Wiprap.
Sorry, what was that?
Wiprap. It's WIPFRAG.
Did you analyze it yourself, or did you send it to Wiprap?
We analyzed it.
How long did it?
I believe, so like just learning the program from scratch, I think we had four results within probably half a day. And now we can take that image and it'll take maybe an hour to do. I think the hardest part, you can edit the delineation of the rock if you don't agree, and then if you saw in that picture earlier, we kind of cut out the parts that were just dirt, and so we just left the rock. So that kind of takes time, but the analysis itself is really quick.
Okay, thank you very much.